This is video 10 for the behavioral analysis series, and this video is just because the last video was a little long. This video, I'm just going to do two examples of using the definition for sequences for convergence to prove that the particular sequence converges to the given value that you're supposed to prove. And so I wrote down the definition. So a sequence AN converges to A if and only if for all real numbers epsilon bigger than 0, there exists a capital N natural number such that for all little n bigger than this capital N, then the absolute value of AN minus A is less than epsilon. So there comes a point where the index value, where you get within the epsilon distance of the limit, and you want to find this sort of where is this cutoff point, and that cutoff point is what capital N is, and then everything beyond that, that's going to be the indices for the terms in which you're within epsilon of the limit A. And the negation of this statement, like the sequence AN does not converge to A if and only if there exists an epsilon bigger than 0, such that for all capital N natural numbers, there exists little n bigger than capital N, where the distance of between AN and A is greater than or equal to epsilon. So the one in green is when you're showing that a sequence does not converge to a particular value. All right, so for these two examples, the first one, we're going to show that the sequence 3n plus 2 over n plus 1 equals 3. And the way I do these is I usually write down this strategy in yellow, and then I'll do the proof in red. That's what it's been for all the videos up to this point. And so for this strategy, I just wrote down, well, what's the definition that we're going to use? And it's, again, for all epsilon, there exists a capital N. For all little n bigger than capital N, then we have the absolute value of the difference. In this case, our sequence AN is 3n plus 2 over n plus 1, and our A value that we're interested in is 3. Okay. And the way these proofs operate is like we sort of work backwards with what our end result is. And our end result is that we want the absolute value of 3n plus 2 over n plus 1 minus 3 to be less than epsilon. And so we sort of work backwards to find n. That's the objective, is to find n. And that's why the last video I called it like a game, called it the NE game. And basically you give me epsilon and then I'll find the corresponding epsilon or corresponding n that sort of depends on epsilon as far as the index value. That guarantees that you're going to be within an epsilon distance of the limit. And I was labeling it as in parentheses epsilon, but I'm just going to write it as just n. So in parentheses epsilon, I'm just going to keep that as capital N. All right, so our objective is we're going to work backwards and find the correct index value for capital N, such that for all the other indices that are beyond capital N, we get the terms to be within the distance of epsilon of the limit. So we start with our absolute value and basically do some algebra. And I just combine it into one fraction. So I made 3 turn it so that it has n plus 1 on its denominator. So you would have to multiply that top and bottom by n plus 1. So it's one fraction. That's why you have 3n plus 2 minus 3 times n plus 1 over the common denominator n plus 1. So then more algebra, you just distribute the negative 3. So 3n and negative 3n cancel out, and you get 2 minus 3, and that's going to be negative 1. So the result of that is the absolute value of negative 1 over n plus 1. Taking the absolute value, that's just 1 over n plus 1. All right, so we want to find n, so greater than capital N. And that implies that 1 over n is less than 1 over capital N. Now, notice that if we have a big number bigger than n plus 1, and we take the reciprocal, then the 1 over n plus 1 is less than 1 over n. So if we start out with a bigger number, take the reciprocal, the 1 over the bigger number is going to be smaller than the 1 over the other number. So that's why I have the inequalities. N plus 1 greater than n, which we want n to be greater than capital N. So I reverse the inequality signs so that I have 1 over n plus 1 less than 1 over n, which is going to be less than 1 over capital N. All right, and that's what we need to find is this capital N, so that we have 1 over capital N to be less than epsilon. So by Archimedean principle, there we know that for all epsilon greater than 0, there exists a natural number, capital N, such that capital N is greater than 1 over epsilon. Well, then that means 1 over capital N is less than epsilon. So essentially, we can have this string of inequalities so that we have this to be less than epsilon. All right, so we found our correct corresponding capital N that goes with the epsilon value. We want capital N to be such that when you take its reciprocal, you get 1 over capital N be less than epsilon. So by Archimedean principle, that value for capital N is going to be bigger than 1 over epsilon. All right, so this is not the proof, this is the strategy. It is going to basically make this all combine everything together, and now when I'll do the actual proof. So let me do that over here. All right, so given epsilon greater than 0, so what are we trying to show? We wish to show there exists a capital N in the natural numbers, so that for all little n bigger than capital N, we have the difference, absolute value of the difference between our sequence, an minus our limit, in this case that we're claiming the limit to be is 3. All right, so this is like our a. So minus 3 is less than epsilon. All right, that's what we need to show. All right, so we're given epsilon greater than 0. So I claim that by Archimedean principle, there exists an n so that this capital N is bigger than 1 over epsilon. Well, then that means that we have 1 over capital N less than epsilon. Okay. So for all n such that for all n such that we have for the natural numbers where it's little n plus 1 that's greater than little n, and we want little n to be bigger than capital N, then we have 1 over n plus 1 is less than 1 over n, which is less than 1 over capital N. And that's true for any natural number. All right, so for the completing the proof, combining everything together, we're going to find n, we're going to use the value n's. Where capital N is bigger than 1 over epsilon. Then for all little n bigger than capital N, we have the following. All right, so the absolute value of our sequence an minus 3. Our sequence is 3n plus 2 over n plus 1. So then that's minus 3. And then we did some algebra, so that's going to be equal to 3n plus 2. And then n plus 1. And then it's one fraction, that's minus 3 times n plus 1. All over n plus 1. And continuing with our algebra, we get that to be equal to negative 1 over n plus 1. Absolute value, that's going to result in just positive 1 over n plus 1. Well, we know 1 over n plus 1 is less than 1 over little n. And we know for our value n such that little n is bigger than capital N, we know that 1 over little n is less than 1 over capital N, which 1 over capital N, that itself is less than epsilon. And that completes the proof. So we found an n, and that capital N is such that it's greater than 1 over epsilon. So we've produced an n such that we get the difference between the sequence for the nth term minus the limit is less than epsilon. So hence, we found an n. So for all little n bigger than capital N, we have that the sequence an minus 3 is less than epsilon. All right, so that is the proof. And then again, I said by Archimedean principle that existence of that capital N is such that we have capital N bigger than 1 over epsilon, which means 1 over capital N is less than epsilon when you take the reciprocals of both sides. Then we know for all little n, n plus 1 is definitely greater than n, little n, which we're saying that little n is going to be greater than capital N. So reverse taking the reciprocal of those, then we have 1 over little n plus 1 less than 1 over little n, which is less than 1 over capital N. All right, so we're going to use this particular capital N in the natural numbers where it's greater than 1 over epsilon. Then for all little n bigger than capital N, we have this following string of, so we have the absolute values of 3n plus 2 over n plus 1 minus 3 being equal to negative 1 over n plus 1, which is, after you take the absolute value, that's positive 1 over n plus 1, which we know that's less than 1 over little n, which 1 over little n is less than 1 over capital N, and we know 1 over capital N is less than epsilon. So that means we found a particular n, capital N, so that for all little n bigger than capital N, the distance or the absolute value of our sequence minus the limit is less than epsilon. All right, so that is the proof. Now here's another example. Now consider the sequence where its nth term is given by an equals 5 minus 1 over n squared. We're going to show that it converges to 5 as n goes to infinity. And again, the strategy is doing this little NE game. I do all this scratch work to find the correct value for capital N that guarantees this particular difference to be less than epsilon. All right, so I just plug in what we have. Our sequence AN is 5 minus 1 over n squared. So that's our AN. And then we have minus A, because that's the limit that we're trying to show. Now, doing that subtraction, the 5 minus 5 cancel out. So then you have negative 1 over n squared. Taking the absolute value, that's 1 over n squared. Well, 1 over n squared is less than or equal to 1 over n. All right, because since n squared is bigger than or equal to n, taking the reciprocal, 1 over n squared is less than or equal to 1 over n. So we're going to, like the similar value for previous proof, we're going to, by Archimedean principle, use capital N greater than 1 over epsilon if and only if that means 1 over capital N is less than epsilon. So we have for little n bigger than capital N, which is bigger than 1 over epsilon. That's if and only if we have 1 over little n less than 1 over capital N, which is 1 over, which is less than epsilon. All right, so we're using the same kind of particular n as last time. So the proof all right, so we start out saying given epsilon greater than 0. I'll do it this time. So for the next couple videos where I say we wish to show, but I won't write it out as in detail. But I think it does sort of help to write it down to reinforce what you're trying to do. We wish to show that there exists a capital N where for all little n bigger than capital N, we have the absolute value of our sequence minus our limit, in this case is 5, to be less than epsilon. All right, so that's what we're trying to show. So by Archimedean principle, we have the fact that there is a capital N where capital N is bigger than 1 over epsilon. And if that's true, then 1 over capital N is less than epsilon. So if and only if 1 over capital N is less than epsilon. Okay, so we know that for all n squared is bigger than n, and we want little n to be bigger than capital N. And that's if and only if. And then this would be greater than or equal to, because we know 1 squared is same as 1. So for all n, we have n squared greater than or equal to n, which we want n to be greater than capital N for our indices. So taking the reciprocal, we have 1 over n squared is less than or equal to 1 over n, and that itself is less than 1 over capital N. All right, so hence, for all little n bigger than this particular capital N that we found, and I'll just go ahead and write it, where capital N is greater than 1 over epsilon, we have, and now we write down our absolute value, and our sequence was 5 minus 1 over n squared. All right, that's our an, and then minus a is 5. So that's equal to, and then we know the 5s subtract out, so you just have negative 1 over n squared, which taking the absolute value, that's 1 over n squared. And we know 1 over n squared, that's less than or equal to 1 over n. And then for this particular n, that's going to be bigger than capital N. We know 1 over little n is less than 1 over capital N. But then we know for this, because we have capital N greater than 1 over epsilon, then we know 1 over capital N is less than epsilon. So this is less than epsilon. So that basically completes the proof. So thus we've found an n such that our sequence an minus the lower limit 5 is less than epsilon for capital N bigger than 1 over epsilon, and for all little n bigger than capital N. Okay, so again, so the scratch work I do first is you try to find the correct value for capital N that goes with the corresponding epsilon. And it happened for both of these examples, it was the same kind of thing. We just used Archimedean principle to have 1 over capital N be less than epsilon, and it worked out for both of these proofs. All right, so that's where I'll stop this video. I just figured I'll do 2 examples where you had to use the definition to find the limit. In the next video, I might do another example and then go into more concepts dealing with sequences.